Do you ever wonder how a computer can look at a picture and not just see a bunch of colors, but actually see a cat or a car or a person? Well, today we're going on a little journey to figure out exactly that. We're going to find out how we teach a machine to see the world, one object at a time.
I mean, think about it for a second. This technology is literally everywhere. It's how a self-driving car knows to stop for a stop sign. It's how your phone's camera instantly puts those little boxes around your friends' faces for a portrait shot. It feels like magic, right? But it's actually just a really brilliant piece of AI. The big question is, how does it all work?
Okay, let's just dive right into the core problem. When you and I look at an image, our brains just get it. We see objects, we see shapes, we understand the context. We see a dog and a cat. But a computer? To a computer, that same image is nothing more than a giant grid of numbers. Each number just represents the color of one tiny little pixel. It has zero understanding of what a dog even is.
So, how in the world do we bridge that massive gap? Well, the solution is a really powerful technique in computer vision called object detection. The whole goal here is to give the computer our human ability to not only see what's in an image, but to pinpoint exactly where it is.
So how do we even begin to teach this digital brain? Well, just like any student, it needs a textbook. And for an AI model, that textbook is built with something we call bounding boxes.
The very first step, and it's absolutely crucial, is called annotation. This is basically the process of us, the humans, going through a ton of images and giving the computer the answers ahead of time. Think of it like you're making flashcards for it. We take a picture, we draw a simple little box around an object, and we label it. This is a cat, this is a dog.
And what's so cool about this slide is you can see that transformation happen right here. On the left, that image is just a meaningless sea of pixels to the AI. But on the right, once we've drawn those boxes and slapped on some labels, it becomes this perfect, valuable piece of training data. It's now a lesson the AI can actually learn from.
And that bounding box is so much more than just a simple square. For the computer, it's a very precise set of data. Each and every box gives it 5 key pieces of information. First, the object's label, like cat. And then 4 numbers that define the box's exact position and size, its central coordinates, its width, and its height.
Okay, so we've created all of our annotated textbooks. Now it is time for the next big phase, training the digital brain itself.
So we take these annotated images and we feed them into a special kind of AI called a deep neural network, or a deep net. The deep net looks at all the pixels that make up the cat, and at the exact same time, it studies the bounding box data we gave it. Its entire job is just to learn the pattern, the relationship between the pixels that look like a cat and the coordinates of the box we drew around it.
Okay, that makes sense for one object at a time. But what happens when you have a really busy scene, with multiple objects, like a cat and a dog in the same picture? How does the model figure out which box belongs to which animal?
And this slide right here illustrates the super clever solution. Instead of trying to understand the whole image at once, the algorithm just breaks it down into a grid. This is the aha moment. It turns one huge, complicated problem into a bunch of smaller, much simpler problems. The AI just has to go to each cell in the grid and ask, hey, is there an object in here?
So how does the system figure out which grid cell is in charge of which object? The rule is actually super simple and kinda elegant. You can see it with the little dots on this slide. An object is officially assigned to the one single grid cell that contains the very center of its bounding box. That's it.
So the really crucial point is that only those 2 center cells are responsible for making a prediction. The cell with the dog center point, it's going to predict the dog's bounding box. The cell with the cat center point predicts the cat's box. And every single other cell in that grid, it just reports back, nope, nothing to see here.
Okay, so we've trained our model on thousands, maybe millions of these grid-based examples. But how do we know if it actually learned anything? Well, just like a student, we have to give it a test, and then we have to grade the results.
And the main way we grade the model is with a metric called intersection over union, or IOU for short. It's really just a score, from 0 to 1, that measures how well the AI's predicted box overlaps with the ground truth box. That's the one we drew ourselves. A score of 1 is a perfect match, and 0 means it completely whiffed.
This slide shows the math perfectly. You just take the area where the 2 boxes overlap, that's the green intersection part, and you divide it by the total area covered by both boxes combined, the gray union part. It's a really smart and honestly intuitive way to score how accurate the prediction's location is.
So once we use IOU to decide if a prediction is correct or not, we start counting up the results. A true positive is a win. The AI found something and got it right. A false positive is when the AI kind of hallucinates and finds an object that isn't actually there. And a false negative, well, that's when it just completely misses an object that was right in front of it.
All right, so after all that teaching, all that training, and all that grading, what can our newly intelligent model actually do? Let's see this thing in action.
And this right here, this is the payoff. A fully trained model can now take brand new images it has never ever seen before and, completely on its own, identify the objects inside and draw accurate bounding boxes around them. It has, for all intents and purposes, learned to see. And we can measure its success with real numbers. Looking at these sample results, this particular model correctly predicted 45 out of 66 total objects on its test. That comes out to a performance score of 68.18%. Not an A+, but that's a solid C for its first exam. It passed.
So let's just do a super quick recap of the entire journey. First, we annotate data to create our textbook. Second, we train a deep net to learn all the patterns using that clever grid system. Third, we evaluate its performance by grading its predictions. And finally, the model is ready to go out and predict objects in the real world.
I mean, from powering self-driving cars to helping doctors spot diseases in medical scans, object detection is completely changing how computers interact with our visual world. And that leaves us with a final thought. Now that computers can see, what's the one area, the one industry you think will be most transformed by giving machines the gift of sight?